Hello, AP students. Today we will be looking at chapter 12, chemical kinetics. And the idea behind kinetics is that you're studying the factors that control the rate, the speed of the reaction. Okay, so as you're watching these podcasts, make sure that you're also reading the chapter in the text and looking at the different examples to get the complete picture pulled together. Okay? So in this chapter, we focus on the forward reaction of a reversible reaction. Okay, I'm going to incorporate a list of objectives for this first podcast using the camera.
The big idea for Chapter 12, Kinetics, is the concepts of collision, molecular collision. So the rates of a chemical reaction are determined by the molecular collisions. So we will always focus on that aspect. Okay, so in our first podcast, the focus is on reaction rates, okay? So reaction rate and instantaneous rate. And your learning goal is to be able to calculate these rates using the changes in concentration and using the stoichiometry of the balanced equation.
Okay, so the vocabulary in this chapter that we will be dealing with is reaction rate and instantaneous rate. And both of these will be defined in the slides. And so let's begin with reaction rates and their calculations. So first of all, what is a reaction rate? Well, it's a way to monitor the speed that the reaction is going by looking at concentration. So it's a change in concentration of a reactant or a product over a certain amount of time. And so you can see in our setup here, in our slide, let's see if we can get a pointer. Yeah, let's see, pointer options. There we go. So you can see in our slide here that the way we show concentration change over time is it looks like this. And that little arrow, triangle there, that little triangle means changing, okay? And then these brackets represent the idea of concentration. And then the units for concentration are molarity, which is the same as moles per liter. So that's big M, okay, for molarity. All right, so let's try a couple of practice problems using the idea of reaction rates in a different fashion.
This is practice problem 24 in your textbook. Okay, and so what we're looking at is the Haber process, a very famous equation, okay, of how you would calculate ammonia. The question is asking us to find out what is the relationship between the rate of the production of this ammonia and the consumption of the hydrogen. Okay, so we're looking at how as this one disappears, this one appears. Okay, and the way you solve these now is you use this equality here. So if you're trying to get a reaction rate using the stoichiometry, the coefficients of a reaction, you simply use this setup and solve it. So again, there we're seeing our delta, our triangles, and our brackets for concentration. Okay, so we're going to use this to equate the rates and make them equal. Notice the negative signs. That represents the idea that that reactant is disappearing, and then the positive signs represent that that reactant or that product is appearing. Okay, and so let's go ahead and solve this one So we're trying to find the rate of production of ammonia compared to hydrogen. So 2 to 3. Okay, so let's go ahead and solve this using the coefficients. Okay, so let's see. Okay, so our change in hydrogen over time, let's try and keep this in front of us, is a 3 to 2 relationship. Okay, so I'm going to put it in as 1 over 3, and then this is disappearing, so I'm going to make it negative. Delta H, concentration over time, is equivalent to, okay, now we're looking at the change in concentration of our ammonia per time. Okay, now this is appearing, so I'm going to put it positive, 1 over 2 delta. Oh, I see my pen is dying. Let me switch it out. Okay. Okay, 1 over 2 over change in time. There, that's better. Okay, and now I want to calculate what is the relationship between the production of ammonia. So I want to know how fast is this forming as this is being used up. So I'm going to solve it in terms of the ammonia. So that means I'm simply bringing this fraction to this side. So how do I do that? I multiply by 2 over 1, cancel, cancel, multiply by 2 over 1. So what do I have? Well, let's get it back up on the screen. So delta, concentration of ammonia, appears or is produced as, let's see, 2/3 of the hydrogen is being consumed. And so the negative, again, showing just being consumed. Okay? So ammonia is produced at a rate to 2/3 the rate of the hydrogen being consumed. And that's how those problems work. So you just have to remember to use this mathematical relationship to solve that. Okay. Here's another practice problem. This is the problem from question 26 of your textbook. Okay, and so again, it's another idea of rate, just a different fashion. So it says, consider this general reaction. So here we go, there it is. And the following average rate data given over some time period. Okay, so here's the decrease of reactants A and B and the increase of reactant C. Determine a set of possible coefficients. So now we're working backwards. We have the rates, and we want to see if we can get the coefficients from this. So these type of problems are just ratios because that's what the coefficients are just ratio relationships. Okay, so you can probably see it just looking at these numbers. But if not, the trick is, let's see, let's just move this up. The trick is to do a ratio here. So let's compare B to A. All right, so, oh, there's the bell. Okay, so as we divide these out or reduce this, we get a 1 to 1.5 relationship. Okay, so B is being consumed 1.5 times faster than A. Okay, now we can't use decimals in our coefficients, so if I multiply this by 2, I have a 3 to 2 relationship of A to B. Okay, well, let's compare A to C. Okay. All right, what do I have here? Here I have a 1 to 2 relationship. So C is forming, I don't know if you can see that, sorry. C is forming twice as fast as A is being used up. So we've got a 1 to 2 relationship there. How about if we compare B to C? Okay, so 0.016 to 0.0120. Okay, let's see, we reduce that, we got a 4 to 3 relationship. Okay, so can we put together some kind of coefficients from this relationship? We've compared them all now, so what I see here is a 2 to 3 to 4 relationship. So if I move those, let's flip that around. So 2A plus 3B produces 4C. And if you come back and look at them, you can kind of see the values now. If you ignore all the zeros, 8 to 12 to 16 is a 2 to 3 to 4. And so that's how you would want to solve determining coefficient type problems. So these aren't super challenging, but they take a bit of thinking about, especially if you're not used to the symbols. Okay, so concentration and change in. Okay, so that's a second type of reaction rate problem.
Okay, in this slide now we're looking at a decomposition reaction of nitrogen dioxide. So here you see it decomposing into these different substances, and we've got some data on each of the substances and how their concentration is changing over time. Okay, and so let's take a moment and let's graph each of these substances so that we can show the concentrations that are decreasing and the concentrations that are increasing. Okay, so here's a graph of each of those concentrations. So the NO2 that's decomposing is decreasing, and then the products, the NO and the O2, are increasing. Okay, now it's possible to find the instantaneous rate. So instead of an average rate like we were first looking at, it's possible to find instantaneous rate. That means the rate at that second in time. And so the way you do that is you simply draw a line tangent to the curve on the graph. So let's say we wanted to know the concentration at this second in time, or this second in time, or this second in time. We would draw a tangent to that point, and then we would calculate the slope by doing rise over run. And then you can find the instantaneous rate at that exact moment. Okay, so this is just an introductory lesson giving you the idea of what a rate is and how to find an instantaneous rate. Okay, the drawing of the tangent to the curve and then calculating the slope by doing rise over run. Okay, so from this podcast, you should have learned what kinetics is. You should have learned the idea of what reaction rate means. You should have learned some symbols, the delta triangle, meaning change in, and the brackets, meaning concentration. And you should know the units of concentration are molarity. And you should be able to calculate reaction rates and instantaneous rates.